Okay, so let's go into this non-dimensional stuff. Recall, we figured out what the maximum velocity was. Square. Okay, that was maximum velocity. We figured out that this was half that maximum velocity. So those two things together, they don't really do much, but right, just make that a 32. Okay, so then from here, solve for the change in pressure from this expression. After we do that, we get the change in pressure. Is this. You just solved it for change in pressure, right? So this is dimensional. Okay, so now we're at the point where I gotta find some pressure. What's a good right? What's a good pressure? So what's a good pressure we should pick to divide this change in pressure to make it non-dimensional? This is pressure and this is pressure because that was all dimensional and works out. But we just want to sweep, right? So we're going to try to figure out a good representative pressure to divide this by to then make our expression non-dimensional and still represent the flow. And we're going to get it from looking at the Bernoulli equation, which seems kind of weird. Because maybe in fluids 1 you said, but wait, Sam, I thought I can't use the Bernoulli's equation if I had a viscous fluid. It was inviscous, incompressible, you get all these things you had to memorize. But fear not, which is kind of cheap. Right, remember that this is what V bar represents, where this is a constant velocity profile. That's what we solved for before, right? So this velocity right here is representing when the inside of the pipe flow is just a constant velocity profile. So constant velocity profiles, this looks like, inviscid flow or frictionless flow if you have no curvature in your velocity profiles. And that's what we solve this V bar for. So it's kind of a cheat, but they allow us to just since we have this idealization of what's going on inside the pipe, let's express Bernoulli's equation, right? So Bernoulli right here says at this point to this point, right? Say that this is the dynamic pressure, gravitational pressure, and then you have just the pressures right there. There's no change in Z, right? Let's say this is just all happening at Z because we're analyzing a straight pipe, okay? So that term's gone, right? If you take from point 1 to point 2, make the subtraction, what do you get? You'll get this. See that this, the dynamic pressure is a good pressure to divide by. And we normally always do that for non-dimensionalizing pressures. We divide by the dynamic pressure that you see in Bernoulli's equation, because it's usually just a characteristic velocity we're screwing anyway, right? In fact, if you took the difference of these two things, this is actually, a V2 squared divided by V1 squared over 2. But we're just doing this after actually small intervals, and we're just going to say this is around some characteristic V prime. So that's kind of the, again, assumptions tricks you're making just so you can invoke the Bernoullis. Okay, so let's go ahead and do that. We just said we realize a nice pressure that we can non-dimensionalize the expression with. So write that out. Right? This is equal to prime delta. I split these squareds up, by the way. Don't worry about that. 2, I'm writing this upside down. And then I had a d prime up top. One of those cancels with one of those. This is, star notation usually means like a non-dimensional quantity. So any quantity to a star is for a non-dimensional quantity. So I might do that a couple times throughout the class. Just remember that's what it is. Move this over here. So that would be diameter of the pipe by the length of the pipe is then equal to what? Well, check it out. 64. Boom. Right? Look at that. It's a Reynolds number. Just coming from the right company. It makes sense for you, but it makes a lot of sense if you do higher level things. But I always thought this was entertaining, at least, that you can do these arguments and you just can like go, look at that, the Reynolds number popped up. And then we do one more thing, and we call this that's what engineers call it. We're going to call this a laminar Darcy friction factor. Hope you see all the motivations to why we get to this thing. We don't quite know how we're using it yet, because that is what actually the next lecture is about. I just want you to not be confused as to what these little F's are. So, big takeaway we learned from our analysis so far is this. Super cool. Super, super cool, I think, right? This non-dimensional pressure thing that we have is a number divided by a Reynolds number. You guys are experts at calculating Reynolds numbers right now, so this isn't too bad. And this is for laminar. That's the end of the story for laminar single straight pipe, right? Next, we want to go that's what we're going to answer next. What about if the flow is turbulent? It's all fine and dandy if it's laminar, but most engineering flows are not laminar, right? In fact, all water piping systems are probably turbulent. Doesn't mean this thing isn't that bad, right? Because the laminar friction factors, those are important for your right, circulatory system, right? All those pipes are super small, so that's actually these Darcy friction factors apply to biological fluid systems. They often just apply to microfluidics, right? Also, is a big one. A lot of money in inkjet printing, right? So you can use this in your career, don't worry. But for this class, because we do water piping systems, we want to figure out what those turbulent friction factors are. That's next.